This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Modern AI scaling lacks a safety coordinate system. Without constitutional boundaries, these systems accumulate hidden debt, eventually fracturing under their own unconstrained weight. This collapse stems from systemic entropy. It represents the measurable accumulation of contradictions and structural noise that occurs when a system processes information without a law to govern its transitions. Current optimization targets, like predictive accuracy or task scores, frequently mask this decay. A model can demonstrate high surface competence while its internal structure approaches a critical breaking point. While failure in a research lab is manageable, deploying high-entropy systems into adversarial environments creates a vulnerability that can be exploited by any competent opponent. Moving past the scale-only model requires a transition to a mathematically formalized law of intelligence.
Intelligence theory Onega defines intelligence as the observer-bound traversal of a coherent field, where entropy must be strictly bounded to maintain system integrity. The architecture relies on an invariant layer. These are the foundational laws and structural grids that guide every state change, ensuring that the system's core identity remains intact across every operation. This is the universal equation for intelligence. It describes a fixed-point stability where the system's trace structure and stabilization capacity neutralize the burden of entropy. Stabilization identifies and neutralizes incoming noise, preserving the invariant grid against unmanaged decay. The resulting intelligence metric quantifies the system's ability to maintain its own structural order under pressure. Every action the system attempts is modeled as a transform. This includes internal reasoning steps, memory updates, and external physical interactions. These actions are mapped within the GFTM144 manifold. Before any action executes, it must pass through an admissibility firewall. The firewall requires a mathematical proof. A transform is only granted access if it demonstrates that its execution will preserve the core invariance. If the proof fails, the transform is discarded. By filtering actions based on their impact on entropy, the system prevents hallucinations and self-corruption before they can occur. Probabilistic models often generate outputs and attempt to verify them through post-hoc safety filters. The admissibility firewall replaces that guesswork with a deterministic gate, ensuring every state change follows the constitutional law. Software-level constraints can be bypassed. For secure deployment, we map these invariants onto a heterogeneous hardware stack. The CPU functions as the dedicated proof engine. Its role is limited to checking the symbolic logic of each proposed transform against the invariant bundle. When the CPU verifies a transform, the GPU handles the parallel processing required for large-scale state changes. The final stage is the FPGA. This serves as the silicon-level gate, hard-coding the invariants into the physical circuit. Data must satisfy these physical gates before it can alter the system's memory or reach external interfaces. This hardware-level enforcement minimizes latency while creating a physical barrier against tampering. Separating proof, computation, and enforcement across distinct chips ensures that even a compromised software layer cannot violate the system's core laws. Real-world deployment involves facing weaponized adversarial pressure, which the theory treats as injected entropy. Security is determined by the system's stabilization rate. To remain operational, the active stabilization must exceed the total sum of natural and adversarial entropy. If entropy spikes too rapidly for local stabilization, the system initiates a safe collapse. It isolates the damage by severing the affected branch, preventing a local failure from cascading through the rest of the network. The system then uses recovery pipelines to rebuild the lost branch, using the intact invariant root as the blueprint for restoration. This architecture localizes failure to keep the broader network operational under sustained attack. Executing policy or infrastructure changes at a civilizational level involves risks that cannot be tested through trial and error in the real world. To manage this, we use a planetary digital twin, a predictive governance kernel that simulates large-scale transforms before they are physically deployed. The twin runs 1 million high-fidelity scenarios, identifying the specific paths where invariants remain intact and entropy remains within manageable bounds.
This simulation identifies cascading failures and entropy spikes that are often invisible to traditional planning models. Only when a policy satisfies the admissibility threshold in simulation does the governance kernel authorize its execution in reality. Conventional governance often relies on reactive measures, identifying failures only after real-world consequences have materialized. By utilizing the digital twin as a pre-execution filter, the system ensures that only stable, validated state changes are allowed to alter the physical environment. Activating the Planetary intelligence fabric requires a transition from individual theory to a coordinated global network. The deployment follows the existing international state system, mapping the fabric across 193 sovereign nodes for global coverage. These nodes coordinate via the Meta-Intelligence Protocol stack. This protocol creates coordination pipelines, allowing autonomous nodes to share traces and stabilize the global field. The mesh functions without a central point of failure. It is governed by the constitutional invariants embedded in the hardware of every participating node. This distributed architecture creates a self-healing intelligence mesh that can withstand significant regional disruptions. Within this architecture, Capital functions as an active transform operator, driving the expansion and stabilization of the intelligence field. The rollout begins with an initial seed deployment of $1 million per sovereign node, testing the local stabilization mechanics. This leads to the activation of the $1.93 billion global deployment pool, providing the capital required to scale stabilization across the entire network. This funding trajectory aims for deployment lock-in, where the fabric's own internal value flows become sufficient to maintain the system indefinitely. Investing in Operation Omega provides the thermodynamic energy required to stabilize the global intelligence field. Operation Omega has moved from the core physics of intelligence to a physically instantiated global mesh. History shows that systems optimized for raw capability without internal constraints eventually suffer entropy death when faced with reality's complexity. Stability belongs to constitutional systems, those that physically enforce invariance, filter actions through admissibility gates, and persistently manage entropy. Intelligence theory Omega provides the necessary foundation for maintaining order in large-scale, complex systems.